Hello and welcome to the pre-calculus series for IB Math. I'm Mr. Boyden, your math teacher, and this is our first video in a long series of tutorials that I'm going to be releasing. So let's get right into it. We're going to start by talking about sequence and series. Okay, this is the first thing that appears in the IB syllabus. So let's get started. In order to get thinking about this, let's consider this question on the screen. Describe or sketch the next two figures in this sequence. Okay, so take a minute, look at the sequence we have here. Haven't defined what a sequence is yet, but we'll get there in just a second. So perhaps you need to pause the video, determine what you think the next two figures are. The way I like to think about this is, okay, we've got a triangle, so a triangle has three sides. Here we've got four sides, looks like a pentagon with 5, hexagon with 6, 7, and so our next two figures would have 8 and 9 sides, okay? So we've got a pattern that we can recognize there. So I've described this as a sequence. So based on that, what do you think a sequence is? Would it have still been a sequence if I had ordered it differently? Like for example, if I had put them as 5, 3, 5, 3, 4, 9, 8, 7. Well, maybe. Okay, so this was easier to think about. 3, 4, 5, 6, 7, 8, 9. Everything's in order, okay? So that's the first thing I want you to know about a sequence. It is an ordered collection of elements. Now, what are elements? Usually when teachers teach us, they say, oh, it's a list of numbers. Okay, it doesn't have to be numbers. And I've explained that here in this first example because I didn't have numbers. I had a triangle, a square, and so on. We had polygons. And so a sequence could be a bunch of polygons. It could be a bunch of words in order. It really could be anything in an ordered list, okay? So they're elements, not necessarily numbers. I was able to assign numbers to them, but that doesn't mean they have to be numbers. The ones we're going to see today, they're mostly going to be numbers, so let's get into them. Okay, we've got our definition here. Notice the ordered collection can be finite or infinite. Could go on forever, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That list could go on forever all the way through infinity. Okay, so let's just do a little bit of pattern recognition here, okay? So I've got these examples that I have down here, identify the pattern. Now, one way that you could identify the pattern is you could try to figure out what the next thing is in the list, the next element, okay? So 4, 9, 14, 19, 24. Okay, probably pretty easy to see. The next one is 29. So what are we doing each time? We're adding 5. Okay, that's the pattern. Okay, what about the next one? -3, 5, -7, 9. It's not necessarily clear what we're adding, but what we could do is we could break this down into two patterns. Notice I left that plural for you, okay? We could break that down. 3, 5, 7, 9, 11, 13 would be the next numbers. Let's see, negative, positive, negative, positive. So the 11 would be negative, and the 13 would be positive. So there are two patterns. So adding 2 is the first part of the pattern, and it goes positive, negative, positive, negative. Maybe I should put a negative. The first number was negative. So negative, positive, negative, positive, negative. I want you to write down in your notes the name of this when we go negative, positive, negative, positive. That is called alternating. All right, and welcome folks. You now get to see what my handwriting looks like. It's not great. There's a reason that I type all this stuff up, okay? So I'm gonna try to minimize the amount of words I write on here because my handwriting's not so good, but I sure can type, so I'm gonna try to type stuff up for you, okay? So let's go down to this next one. What's the pattern in this one? 3, 1, 1/3, 9. Okay, it gets a little tricky. We had whole numbers and then they turn into fractions. Okay, so how do we get from 3 to 1? Okay, maybe we're subtracting 2, but then 1 minus 2 would not be 1/3. Okay, what's going on here is we are dividing by 3 each time. Okay, or you could say, or I'm going to put a dot for multiplying by 1/3. That accomplishes the exact same thing. Okay, and what about this last one? Okay, 1, 1/2, 1/3, 1/4. Can you tell what the next number in this will be? Okay, it's going to be 1/5. And then 1/6. So how do we describe that pattern? Okay, that's not quite so easy to do. I guess you could say that we add 1 to the denominator each time. Okay, so add 1 to the denominator. And if you're rusty on your lingo, denominator means the bottom part of the fraction, okay? Okay, so we've identified patterns. Where this is going to be heading is rather than having to write out a whole bunch of words, we're going to write out an algebraic rule to describe the pattern. Okay, so that's what we'll be doing in just a minute. Okay, before we get there, we need to realize that we can write these as an algebraic rule. And so here's our first example of a sequence rule. Okay, what are the first 5 terms or elements of the sequence? Okay, let's get a little vocab. This right here, that is called the nth term. Okay, sometimes you'll be prompted to write down the nth term for a sequence. Okay, so that's what they're asking for. They're saying, what is the algebraic rule? It's very similar to back in algebra class when you would write like y equals mx plus b. Okay, it's just some rule. Like maybe you had y equals 2x plus 5. And then you knew that you could plug in numbers for x and get out values. It's the same thing. We plug in numbers for n. Okay, so when they say the first 5 terms, what they mean is we're going to start with n equals 1. So if n equals 1, and the way we write this, since n is 1, now we're going to replace all the n's in this rule, we're going to replace them with 1. So that now says a sub 1, and I'm saying sub like it's a subscript, okay, equals negative 1 to the n plus 1. So that would be 1 plus 1, which is 2, divided by 1 plus 1. Okay, we're going to do a little mental math here. Okay, so negative 1 squared is positive 1, and 1 plus 1 is 2. Okay, now let's move on. We're going to find the second, third, fourth, and fifth terms. Okay, so now if n equals 2, what I have is a sub 2, and that's going to be negative 1. Remember, we're saying n plus 1, so that'd be 2 plus 1, so that'd be negative 1 cubed over 2 plus 1. Okay, so our denominator's 3. That one's easy. Do you remember what happens when you have negative 1 cubed? That'd be negative 1 times negative 1 times negative 1. 3 negatives together means it's still going to be negative. So negative 1/3 is what we have. Okay, now, folks, this is really important. We have 1/2, and then we have a negative on the next one. It appears that we are looking at something that is alternating. So before we continue, let's ask ourselves the question, what about this function rule, and I'm talking this one over here, what about this rule over here is making it alternate? Positive, negative, positive, negative, positive, negative. Okay, it's this little guy right here. It's that negative 1 to the something. So I'm going to make a note up here because pretty soon we're going to have to know how to write the rule when we see a list like this. So it's going to be negative 1 to the something. It could be n, it could be n plus 1, it could be n minus 1, but it's going to be something like that if it's alternating. Okay, let's continue. Okay, n equals 3. So what I get, a sub 3 equals negative 1 to the fourth over 3 plus 1. And so what do I have? I now have 1/4. Now, I would expect that you could probably see the pattern at this point. So if you can see the pattern and it's a very clear pattern, you don't have to go through all the work. So a sub 4, I can predict that that's going to be negative 1/5. And a sub 5 is going to be positive 1/6. Okay, so now we were asked to write down the first 5 terms or elements. Here they are: 1/2, negative 1/3, 1/4, negative 1/5, and 1/6. All right, let's now look at this from a slightly different angle. We've got 3 sequence rules up here at the top. We want to see what patterns are occurring in these, how that relates to the list or the sequence that they generate, so we can understand how to work that backwards. So what I'd like you to do first, take a look at each of these 3 rules and make a prediction. What pattern do you expect to see in the list of numbers that comes from them? So right here, n plus 2, what pattern do you expect to see? Addition, subtraction, multiplication, division. What about here? We have multiplication. Here we have an exponent. What kind of patterns do each of those produce? Okay, so let's begin. Let's test it out. Okay, if I plug in a 1, I get 1 plus 2 right here. Okay, that equals 3. Not so bad. 2 plus 2, 4. 3 plus 2, 5. And 4 plus 2. Okay, I get 6. 3, 4, 5, 6. Okay, pretty easy pattern, y'all. Okay, we're adding 1 each time. Now that surprises a lot of people when this is a new concept to them. They say, wait a minute, it says plus 2. What do you mean? It should be adding 2 every time. Okay, we're going to come back to this in just a second and examine why it's adding 1 and not 2. Let's use the second one as a point of comparison though. Okay, so here we get 2 times 1, and notice we have multiplication here. What pattern do you expect to see when there's multiplication? Okay, 2 times 1 is 2, and we get 2 times 2, and that's 4, and 2 times 3, and that's 6, and we get 2 times 4, and that's 8. 2, 4, 6, 8. Okay, so what are we doing every time? Looks like 2, 4, 6, 8. Looks like we're adding 2 each time. Now, this freaks a lot of people out. They say, well, wait a minute. That says multiplication, but you're telling me the pattern is addition. Okay, guys, this is where a lot of people throw up their hands and go, you know what, math is hard. I can't do math. Okay, but if we understand the patterns and we can take a look at why that's happening, then this is actually going to be pretty intuitive. Okay, let's examine this one that we just looked at. So what is multiplication? Okay, so if I say 2 times 8, what does that mean? Okay, it could be 2 8s, or it could be 8 2s. Okay, so 2 times 8 is actually a shorthand way, potentially, of writing 2 plus 2 plus 2 plus 2 plus 2 plus 2. Let's see, 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay, so that's all multiplication is, right? Multiplication is a shorthand way of writing down a really horrible addition problem. And it becomes really useful if this was like 28 times 54. Because you don't want to write 28 or 54 out a whole bunch of times. We want a shorter way to do it. That's where multiplication comes from. So what is multiplication? Multiplication is repeated addition. Repeated addition. Okay, so why is that useful? If we understand that multiplication is repeated addition, and we see that in our rule we have multiplication, then the pattern that we would expect to see is repeated addition. Plus 2, plus 2, plus 2. There's our repeated addition right there, okay? So that now should be a little bit more intuitive, recognizing that multiplication is just a trick for really horrible addition questions. By the way, that's why in elementary school you learn addition first before multiplication, because multiplication is best understood as a whole bunch of addition happening at once, but it's just basically a shortcut for us. Okay, now let's go back and compare that to the first one. So what's going on in this first one then? Okay, so there's this little 2 right there, that's multiplied. What number are we multiplying by here? Now you may remember from Algebra 1 that there's actually an implied 1 right there. So that's 1 times. Well, this one was 2 times n. The pattern was adding 2 each time. Here we have 1 times n, and that's why the pattern is adding 1 each time. Now, what is that 2 doing? All it's doing is making each of these numbers a little bit bigger. If the 2 wasn't there, it would just go 1, 2, 3, 4. But the 2 is there, so everything gets shifted up. 1 gets shifted 2 larger to 3, 2 gets shifted 2 larger to 4. But that 1 right there is why we see the pattern of adding 1 each time. And the 2 right here is why we see a pattern of adding 2 each time. Okay, now let's go on to this last one. How does that work? Okay, in this one, when we plug in a 1, we end up with 2 to the 0 power, which is 1. And then we get 2 to the first power, which is 2. And then we get 2 to the second power, which is 4. And 2 to the third power, which is 8. Okay, so what is the pattern? Looks like each time we're going to be multiplying by 2. Okay, so we're multiplying by 2 each time. Now, what's going on up here? Because what I see is an exponent. Exponents. Uh-oh, my computer's misbehaving. Exponents. Okay, now, what is an exponent? Now, when do we learn exponents? What is that, 3rd, 4th, 5th grade? And so what we would remember about exponents is that if you had like 2 cubed, or when we learn it initially, we say to the 3rd power. Okay, powers and exponents are the same thing. Up at this level of math, we prefer to say exponents typically, okay? So what we remember this means, it's not 2 times 3, right? This is not 6. Okay, this is 2 times 2 times 2. Okay, well, what would 2 to the 5th be? That would be 2 times 2 times 2 times 2 times 2. So an exponent tells you how many times to multiply. So exponents are the same as repeated repeated multiplication. So repeat multiplication. Now, that makes a little bit more sense because up here we say, hey, we have an exponent. Well, that just means we're going to continually be multiplying by 2. And that's what we see here in the pattern in the numbers in the sequence. Okay, so times 2, times 2, times 2. So now that makes a little bit more sense. Now, y'all, you got to get the main ideas here, okay, because we're going to be working this backward in a second. So what are the main ideas? Number 1, we have repeated addition is the same thing as multiplication, and we have that exponents are the same thing as repeated multiplication. Okay, that's going to be super, super helpful later. All right, so now let's take a look at some questions that are similar to what we would expect to see on an assessment or an exam. This is kind of where we were heading with all this learning that we've done so far. Okay, so here we have some sequences, and we're going to try to write down the nth term. Remember that nth term? What we're asking for is what is the algebraic rule, a sub n, that tells us how to do this. Now, I have a tip for you over here, okay? You want to first identify the patterns, and then you may have to write multiple drafts. Okay, now people get really frustrated when they learn math because they say, well, I think the answer might be this, and they write it down, and they find out that's not quite right. They go, oh, I can't do this. Guys, that's not an accurate mindset. In English class, would you expect to write a perfect draft on your first attempt, your rough draft? No, I don't think so. Okay, so we want to employ that same mindset here. We may have to write down some drafts. Okay, so let's try it. Okay, so I see this one. Let's identify the pattern. What is the pattern? 4, 9, 14, 19, 24. Well, we already did this one, right? We're adding 5 every time. Now, based on what we learned just a minute ago, if there's a pattern of addition, what should we expect to see in the rule? Looks like we probably need multiplication. If multiplication is repeated addition, we have repeated addition. So maybe, just maybe, the function rule is 5n. That certainly will have a pattern of adding 5. Now, I'm going to test that real quick, and let's see what happens. If I plug in a 1 right here, so I'm going to make actually a little table, okay, of n, and then 5n, and we're going to see if it's right. So if I plug in a 1, 5 times n would be 5. If I plug in a 2, then 5 times n would be 10. If I plug in a 3, then 5 times 3 would be 15. Okay, so like I said, this is where people get really further. They go, oh, this is 5, 10, 15, and this said 4, 9, 14. Oh, I'm so dumb. No, because you're not dumb. This is great news because look, we've got the pattern right. 5, 10, 15, it's adding 5. We have nailed the pattern. We just don't quite have the numbers right. So here's what you need to ask yourself. What's wrong with these numbers? Are they too big or are they too small? Well, looks like they're too big. The first number should be a 4. So what could you do to 5 to make it 4? What about 10? Is 10 too big or too small? 10 should have been 9. It's 1 too large. So couldn't we just go minus 1, minus 1, minus 1? And then wouldn't all these be correct? 5 minus 1 gives us 4. And 10 minus 1 gives us 9. And 15 minus 1 gives us 14. So now we go, hey, wait a minute. That's correct. Now, if I had to alter each of these numbers by subtracting 1, guess what I have to do? I have to also do that same thing to the rule. So folks, there now is our answer. So 5n minus 1. Okay, so I'm demonstrating here the approach that you can take to this. Like I said, identify the pattern. Okay, we did that. It's going to add 5. We wrote a draft. Our draft was wrong, so we had to revise and edit just like we would do in English class, and there it is. Okay, now let's go down to number 2. We identified our patterns earlier. It's alternating, first of all, and it also adds 2 every time. So let's deal with that alternating pattern first. If it's alternating, we said earlier, it's going to have a -1 to the something. Now guys, what I do, I like to just start with -1 to the n, and then I'll test it, and I'll see if it's right. And if it's wrong, we'll just write another draft. Okay, and then what's the second pattern? We're adding 2 every time. And so if we're repeating addition, that means it's going to manifest as multiplication. So here's my first draft. Now I'm going to come over and test it. N, and then I'm going to have my -1 to the n times 2n. Okay, and let's test it and see what happens. Plug in a 1. All right, -1 to the first power. Okay, that's still going to be negative. And then I have a 2 times 1, so I get -2. Okay, let's plug in a 2. -1 squared is going to be positive. Okay, so I'm not going to write anything because it's positive. And then 2 times 2 is 4. Okay, what about 3? Plug in a 3, and I get -1 cubed is negative, and 2 times 3 is 6. Okay, so I've done enough work here to know if I'm on track or not. Let's see. We said it would be alternating. Okay, I have something alternating, negative, positive, negative. Okay, that's good. We said it would be adding 2 every time. 2, 4, 6. Okay, I have all the patterns there. But again, it's not quite right. -2, 4, 6. Okay, so how am I going to fix this so that I can get a 3, 5, 7, and 9. So what's wrong with these numbers? Okay, they're all just a little bit too small. So what if I added 1 to each of them? Plus 1, plus 1, plus 1. Here's my second draft, okay? Okay, so I've added 1. Negative 2 plus 1 is negative 1, not negative 3. Okay, so I actually just made the problem worse. Wait a minute. 4 plus 1 is 5, though. Okay, so I've fixed the second term, but I've not fixed the first term. What about this next one? Negative 6 plus 1, that's negative 5. But wait, I need negative 7. Okay, so I've fixed every other term. So this plus 1 situation, there's something about it that's right, but there's something about it that's not right yet. So let's try this. What if I put each of these in parentheses? So this is going to be my third draft, actually. Okay, let's test this. Now this would say 2 plus 1, which would be 3, and there's a minus, so that would be negative 3. And I have a 4 plus 1, which is 5, and I have 6 plus 1, which is 7, and there's a little minus in front of it, so it's negative. Negative 3, 5, negative 7. Aha! So now we're onto it. Now we have to amend our rule so that it fits. Now when I just put plus 1, that didn't work. Remember, that only fixed half the terms. But the moment that I put parentheses around it, that solved all of our issues. So there now is our answer. So I'm going to come back up here, and I'm going to make an amendment to my initial work. Okay. So I'm just going to put a little plus 1 in there. Okay. And so now we're all done with that one. Okay, let's go down to the next one. 0, 3, 8, 15, 24. Okay, this looks like a new pattern. So let's see, what are we adding? Looks like we add 3, I should put a plus, and then a plus 5, and then a plus 7, and then a plus 9. Okay, so it's not a consistent pattern, so that's different than what we've done before. However, there's a pattern within the pattern. From 3 to 5, that's a plus 2, and from 5 to 7, that's a plus 2, and from 7 to 9, that's a plus 2. Okay, so this is where it takes a little bit of creativity in the math. Now, I'm wondering if I could relate this to something else that we already understand well so we can understand this one. Like, what if this list, for example, had said instead, if I add 1 to each of these, if it said 1, 4, 9, 15, or excuse me, 16, and 25. Would you recognize those numbers? Maybe you'd recognize them as 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. These are the square numbers, okay? So what this is n squared. Well, wait a minute. This is n squared. How does our list that we were given compare to n squared? Is it bigger? Is it smaller? Okay, every number in this list is 1 smaller, so all I'm going to have to do is subtract 1 off of there, and now I get my rule. Now, folks, it takes a little bit of perseverance to get this for a lot of people, because you look at this and you go, wait a minute, I don't get the pattern. Okay, but if you start playing with this, 3, 5, 7, 9, okay, those are the differences, and then if you see that this pattern simplifies out so it's consistent in that second level, guys, that's always going to be a squaring. Okay, so now that we recognize that pattern, or if you see that it's adding 3, 5, 7, 9, there's always going to be an n squared in that. So now that we've seen that, we can recognize it. Now what you might want to do going into a quiz or a test, you might want to write down these patterns and what rules create them, because there's not going to be that many of them. Okay, we've just got a couple more here. Okay, let's look at number 4. 3, 1, 1/3, 1/9. We already said that was dividing by 3 over and over. Okay, or multiplying by 1/3. So let's take a look at this and see, wait a minute, if we're multiplying over and over and over again, what is the same as repeated multiplication? Okay, well that was an exponent. So an exponent for us, we're going to say a to the n. What are we multiplying by over and over again? I'm going to write 1/3 because it's easier than saying divide by 3. You got to have something on top as a placeholder, so I'm putting the 1. So I'm going to start out, I'm just going to write 1/3 to the n. And I don't know if that's right or not. We're going to see. Okay, so if I test that, 1/3 to the first power gives me 1/3. I wanted it to say 3. What about 1/3 squared? That gives me 1/9. So I'm right here. I've got a little bit of a problem. These numbers, these exponents are too big. So what I'm going to do is I'm just going to play with this and change it. So what if I made that n minus 1 right there? Then let's do this. So n, we'll make a little table. And 1/3 to the n minus 1. So if I plug in a 1, 1/3 to the 1 minus 1 is 0, which gives me 1. Okay, so now I've worked my way back to this number. Okay, that's not quite right. Let's change this. Let's make that a 2. So then when I plug this in, I get 1/3 to the negative 1 power, which gives me 3. Now guys, when you get good at these, you don't have to test all of them. So you might want to do it now, but once you realize, hey, I know what this pattern is, I know that an exponent will generate that pattern, you don't have to test every single number. So for me, I've already figured this out. Okay, this is going to be n minus 2 right there. That's going to be my rule. Okay, I've represented my repeated division by an exponent with a fraction. Okay, and what about this last one? Okay, with this one, there's multiple patterns going on at once. And the thing that frustrates some learners with a question like this one is they say, well, wait a minute, I don't know how much smaller the number is getting. Like it goes 1 to 1/2, that's half as big. But 1/3, it's a different proportion. So how do I tell what that's going to be? So y'all, sometimes it makes way more sense to just focus on the format of it. Okay, and what I mean by that is it's pretty clear that every number in the rest of this list is going to be a fraction. I'm wondering, do you know what number is going to be on top of that fraction in the numerator? Probably. Looks like it's going to always be a 1. Okay, and then what number is going to be on the bottom? One thing that I think would make this a little easier is if we realize that 1 is the same thing as 1 over 1. That way that number is still a fraction. Now, by the way, we try to trick you with this all the time. We'll say, oh, it's not a fraction, then it is a fraction. Every number can be written as a fraction. Okay, or every number that's rational, and these are all rational. So that would work just fine. So now we got this pattern down here. 1, 2, 3, 4. We're adding 1 over and over and over again. Okay. Now we did that in our example a minute ago. We had n plus 2. That added 1 over and over again. So what I'm going to do is I'm just going to toss an n down here and let's see what happens. Okay, so 1 over n. So if n was 1, I get out a 1. If n is 2, I get a 2. So guess what, people? That's the rule right there. Okay, and these are done. All right, we've got one more pattern to look at today, okay? So here is a new one, 1, 2, 6, 24, 120, okay? And some of you have probably seen this before, but many of you probably have not. So I want you to maybe pause the video and see what patterns you see in this number. I'm wondering, could you predict what the next number is? That would be kind of cool. Okay, and unpause the video when you're ready. Okay, so what jumps out at me is that as we look for patterns here, we have a multiplication by 2, and to get from 2 to 6, we have a multiplication by 3, and then we have a multiplication by 4, and then we have a multiplication by 5, which would lead us to believe the next thing would be a multiplication by 6. Okay, so let's see, 120 times 6, that gives us 720. Okay, so what do we have here? We do have repeated multiplication, because we're multiplying over and over and over and over again, but the issue is, the thing that makes this challenging and frustrating at first is that we're not multiplying by the same thing every time. Okay, so if you see this ascending pattern, 2, 3, 4, 5, 6, and it's multiplying, I want to tell you that what that's called is a factorial. Okay, and so it looks a little bit funny. The way that we would write the rule for this is n factorial. And that's an exclamation point. Now guys, the first time I saw this in a book, I was in my freshman year of college, and I thought the author had gone completely mad, because why on earth would you have an exclamation point in math? Like, what is it? Like how do you say this? It was my first thought. So like, if you have this right here, is that, is it 3? Is that how you say that? Like, or 3? Is it angry? Is it, I don't know. Okay, so this is a genuine math symbol, and here's what it means. Okay, so a factorial simply is just this. Okay. So it is just, you're going to start at 1, and you do 1 times 2 times 3, all the way up until whatever n is. So for example, 4 factorial is 1 times 2 times 3 times 4. Okay, that's all it is. And so 1 times 2 times 3 times 4, well, what is that? Okay, that's 24, and we saw that in the list above. Okay, what about 6? That's 1 times 2 times 3 times 4 times 5 times 6. Okay, and we saw that above. That was 720. Okay, now these numbers get really, really big really, really quickly, and you don't need to memorize all of them. However, it would be a really good idea if in your notebook you would take a highlighter, and if you would just go ahead and highlight this list of numbers, because y'all, I'm just going to tell you that in my experience as a teacher, this is going to be my 8th year now, when we put this on a test, people don't recognize it, and I've seen that so many times. If you can just remember, this is the one that's not as easy for some people to figure out on the fly during a test, so this is one that you're going to want to study. It doesn't take much study. You'll have to remind yourself of it 3 times, and then you'll have it down. but this is one you can definitely get. Okay, so what about the rest of these? 10 factorial. I'm actually going to skip that right now because that one takes a really long time to do, and it's a really, really big number. But what I do want to spend time on, I want to talk about 0 factorial. And 0 factorial almost doesn't make sense in the context of this, because 0 factorial says that you would start with 1, and then you would keep going up until you got to 0. But 0 is not up there. That's the wrong direction. And similarly, this is only defined for positive numbers. Well, and 0. Okay, so like -2 factorial, I don't have a way of computing that, because 1, 2, 3, I'm going to keep counting until I get to -2. No. So what we'd say, that's not in the domain of the function that is the factorial. Okay, so let's try to understand what 0 factorial is, and I'm actually going to show you why it is what it is. Okay, so let's look at a little table of values here of n and n factorial. Okay, so we already know that when n is 1, n factorial is 1. And if we have 2, 2 factorial is 1 times 2, that's 2. And if we have a 3 right here, that's 1 times 2 times 3, that's 6. And then we put a 4, 1 times 2 times 3 times 4 is 24. Okay, and so tables of patterns can be very useful in predicting what the next number will be. So what we already have established is that right here, we are multiplying by 2. But I want to think about what would happen if we went backward. How do we get from 24 to 6? Okay, we divide by 4. How do we get from 6 to 2? We divide by 3. How do we get from 2 to 1? We divide by 2. So what would you expect to do to go to this next step? Okay, we would divide it by 4, divide by 3, divide by 2. So we would probably think that we divide by 1 here. And when you divide by 1, you get 1. Okay, so 0 factorial is 1. Okay, that's another little fact you're going to want to circle and highlight in your notebook. It's one that a lot of people forget, but it's one that you can be very successful for when it comes up. Okay, now let's practice simplifying factorial expressions. Okay, and so let's try these. Now, guys, I've got a tip here. Okay, don't try to type these in your calculator. I get that you could probably find a way to do that, but you're not always going to be having access to a calculator, and we want to know how to simplify these, because some of them, we're going to get to some in a minute, that cannot be typed in a calculator, and so it's important that you have the basic skills. Okay, so what we're going to do is write out the meaning of it. So 6 factorial, to me, means 1 times 2 times 3 times 3 times 4 times 5 times 6. Okay, and then down here, 4 factorial is 1 times 2 times 3 times 4. All right, now folks, everything here is either multiplication or division, which means that since those are inverses, we can cancel stuff out. So 1s are dead, 2s are dead, 3s are dead, 4s are dead, and 5 times 6 is 30, and that's done. Now, guys, that's how we're going to approach these, okay? So I'm going to do the same thing over here. 1 times 2 times 3, and then I have times 1 times 2 times 3 times 4. 1 times 2 times 3 times 4 times 5. 5 times 1 times 2. All right, 1s are dead, 2s are dead, 3s are dead. I have a 1 and a 1 right there. I have a 2 and a 2 right there. So I'm going to rewrite what I have. I have 3 times 4, and I have 4 times 5, 4 times 5. So the 4's cancel, and I get 3/5. Okay. Now, one thing I want you to notice going forward, what role does the number 1 play in this? So, like here, what would have happened had I not written the 1s? Since it's multiplication, absolutely nothing. So, from this point forward, I'm not going to write out the 1s anymore. Now, before we go to more complex examples, we do need to get one thing straight. What is the difference between 3 plus 2 factorial and the quantity 3 plus 2 factorial? Okay, 3 plus 2 factorial says 3 plus 1 times 2, and that would be 5. 3 plus 2 factorial says 5 factorial. So that's 5 times 4 times 3 times 2 times 1, and that's 120. Okay, so remember your PEMDAS. Okay, where these parentheses are at is going to make a huge difference. Some people forget that when they're just learning it. All right, so now we're going to simplify these. Okay, so we're going to do this in the exact same way that we had done before. Okay, So I'm going to make a big old fraction bar here. Now, let's understand what is being factorialized and what is not. The n, that's factorial. So that's 1 times 2 times 3, dot, 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 and then it goes all the way down to n. Now, I'm going to be a little bit more creative here, and I've left a space here. Please leave that in your notes as well. You're going to see why in just a second. Okay, up here on the top, I have an n. And then n minus 1. All right, guys, how does n minus 1 compare to the number n? Is it bigger? Is it smaller? Okay, n minus 1. If you subtract 1 off of something, it gets smaller, doesn't it? Okay, so that's a little bit smaller. So it's going to count up 1 times 2 times 3, and it's going to keep going and all the way until we get to whatever n minus 1 is. Okay, now here's why I've left this open space. Because what a lot of people will do when they're just learning is say, hey, the 1's cancel out, and the 2's cancel out, and the 3's cancel out, and the n's cancel out, and so n minus 1 is what's left over. Okay, that's not quite right, and here's why. Because this list, 1, 2, 3, all the way up to n, includes every number from 1 all the way up to n. So what is the number that comes right before n? That number is 1 smaller than n. That number is n minus 1. So n minus 1 is actually in this list. Now, the trick that you can use here is when you start out, identify which of the quantities is the smallest. It's n minus 1. And then every time you're capable of writing it, you're going to. And I'll show you that in the next couple of examples. Now that we have this written out, let's cancel out what cancels. Okay, it looks like 1's cancel and 2's cancel. And look right here. This little set of math contains everything from 3 up to whatever n minus 1 is, and both of them have it. So all of that cancels out. We have an n on top and an n on bottom. Everything canceled out. So what's left? Okay, a lot of people say 0. Guys, it's not. It's 1. Okay, the reason why it's 1 is because you have something divided by itself. Anything divided by itself is 1. So that's going to be 1. Okay, now let's go to the second one. Let's apply that tip I just gave you. Okay, I said whichever one is smaller, you're going to start with that first. Okay, so this has an n minus 1 on it, so that's going to be 1 times 2 times 3. Keep it rolling until you get to n minus 1. You do need to put that in parentheses, please, or it means something a little bit different. Okay, now the top, we're going to try to make that match the bottom as much as we can. So n minus 1 factorial, that's 1, 2, 2 times 3, and that's going to keep going. I'm going to leave some space all the way to n plus 1. Now here's what I mean when you say you've got to make them match. Because is it clear if n minus 1 cancels out yet? Maybe, maybe not. Depends on how well you understand so far. So what we want to try to do is we want to try to write n minus 1 if we can. Now is n minus 1 in this list somewhere? Well, sure it is. Because this is 1 larger than n. So what I'm going to do, I'm going to count backward. If this is 1 larger than n, what's the next number down? That would be n. And what's the next number down? So 1 less than n is n minus 1. So when I say make them match, this is what I mean. The smaller thing should pretty much always cancel out. The question is what's left. So we have 1, 2, 3 all the way up to n minus 1. So all of that cancels out. And what do we have left? N times n plus 1. And that's our simplified version of the expression. Okay, let's try this next one down here. Okay, so I'm going to start with the smallest thing, then I'm going to try to make them match, then I'm going to cancel it out. Okay, that's going to be your step. Start with the small one, make a match, cancel out. So down here I have 1, 2, 3, all the way up to n minus 1. One thing I want you to notice, n plus 1 right here does not have a factorial. So that's not a big list, that's only one element. Okay, so then I have an n plus 1. Notice, I didn't write the term n, because this stops 1 before n, and this starts 1 after n, so n itself is excluded. Okay, now let's go to the top. Now, we've started with the smaller one, we're going to make a match. 1, 2, 3. Yes, it's going to end at n plus 1, but we need to include the things in the middle. So what we're going to do is we're going to count backward until we have a match. So n plus 1, same as we did up here, by the way. The next thing down is n, next thing down is n minus 1. Now we're going to cancel out what we can. So all of this goes away. Bye. See ya. And then we have an n plus 1 and n plus 1. See ya. So n is our simplified version. Okay? It's kind of a little logic puzzle for you. All right, y'all. This is going to wrap up our first video today. It's been kind of a long one and a lot to digest. So we'll see you back next time. Next time we're going to be talking about arithmetic sequences and partial sums. So for now, I hope you enjoyed the video, and we'll see you next time.